So, Joule's law and electric power. So we've said that as charges flow through a circuit device, like a resistor or a light bulb or iPod or whatever electric device, they lose energy due to collisions with atoms in the wire. They lose energy due to collisions with atoms in a wire. You end up with you start with a higher voltage, you lose energy, and you end with a lower voltage. Wait a minute, Mr. Dueck, you said you lose energy. Voltage is measured in volts. Remember, voltage is energy per coulomb. So if you've lost voltage, you haven't lost coulombs, you've lost some energy per coulomb. This energy is transformed into heat, and we're very clever. We can do an awful lot with that heat. So the energy lost by charges is related to voltage drop because we said that potential energy was equal to QV from last unit. We actually defined voltage to be how much energy there was lost or gained or per coulomb. This is always going to be a loss, Luna, going through a resistor, okay? And what we're going to try and come up with now is an equation for how much power you lose going through a resistor. So this is power loss. We're not going to call it a loss every time we're going to clue in. If we're talking about a resistor, you are losing energy. Power is energy loss over time. So power is QV over time. And now I've found a way at least to get some electric components into my work or change in it. Because remember, energy is the ability to do work. So QV, which is energy, is also the ability to do work. I can put it in for work. I've found a way to get that into my power equation. And then right here, it says grouping. That's grouping, Jake, not groping. Grouping. It says grouping. What I'm going to do is I'm going to rewrite this equation. I'm going to put the V first. And then I'm going to put the Q over T like that. I'm just going to group these. I'm going to just emphasize, although the T is underneath both of them, I'm going to move it underneath the Q because Q over T is something from lesson 1. That's our first equation. Do you remember what Q over T was? And if you're not sure, you can look down one line in brackets. What? Current, I. Okay? So, this is Joule's law. Power equals V times I. We call this Joule's law. Named after a scientist whose last name was Joule. Also got a unit named after him. Power is equal to the energy drop per coulomb of charge times coulombs of charge per second. You know what? It's voltage times current. That's power loss when you're going through a resistor. That's the one that's on your formula sheet. In fact, that's the one we're going to put into the little box here. What that's done is that's given us so far 3 equations. We started out defining current. We said current was equal to Q over T, but I'll be honest, we're not going to use that again until the test. I will ask you one question on the test where I either, well, there's 3 things in that equation. I'll either give you Q or T or 2 of them and find the third one. But the ones we're going to be using, I'm going to put them in red because they're so important, is this one, what we called Ohm's law, and this one, Joule's law. So the 2 red equations, ignore the blue one, the 2 red equations, how many variables grand total are there? How many different variables? Count. 4. If you know any 2, you know 4. In fact, that's a phrase I'm going to be flogging to death for the remainder of the unit. If you know 2 things, you know 4 things. If you know 2 things, you know 4 things. In fact, that's going to guide much of our strategy when we start to analyze circuits and fill in the blanks. What we're going to look for, one of the things is there any resistor where they told me 2 things? Because if they told me 2 things, you know what? I actually know 4. Is there anywhere in the circuit where they told me 2 things? You know what? I actually know 4 things there. In fact, we can combine these 2 to get 2 more versions of Joule's law. These next 2 are not on your formula sheet, but I'll show you them anyways. So, what did we just say, Jake? Power equals what times what? Except what's another expression for V? Oh, so another way to write this would be power equals I R I. But that's really I times I. What's another easier way to write I times I? Okay. Honestly, even though this one is not on my formula sheet, I always end up memorizing this one during this unit because it's the one that I use the most, just because most of the time it seems when I'm analyzing a circuit, I happen to know the current at that location and the resistance at that location. But Justice, it is redundant, because if I know the current and the resistance, I could find the voltage very easily and then use VI. So you don't have to memorize it. It's redundant. But you'll see when you're looking at my answer keys, for example, I often pull it out without showing all the steps. I just happen to have it up here. And then after I finish this unit, it's forgotten again. Well, there's an I right here. There's an I right. Kyle, could you get the I by itself from this equation here? Could you rewrite this equation in terms of I? I equals. So you know what? Another way to write this would be V times V divided by R. Except instead of writing VV, what's a nicer way to write? Okay. That's another version of Joule's law. I think there's 2 questions that I recall using it for, but almost never. And again, Rachel, it's redundant because if you give me the voltage and you give me the resistance, I can find the current using Ohm's law and then use VI, the one on my formula sheet. So both of these 2 here are redundant. The left one, it's useful just because it seems to pop up the most. So you can survive without them. Of course, that brings me to my comic. Circuitry. Spider-Man fans will get this. Remember, with great power comes great current squared times resistance. Ohms never forgot his dying uncle's advice. What's the Spider-Man joke? When Uncle Ben dies, what does he say to Peter Parker? With great power comes great responsibility. Well, he said it wrong. It really should have been current squared times resistance. Okay, we're back. Technical comment here. Don't need to know this, but nerd. Really, if we're talking about energy lost due to particles, I really do the charges going through the resistance. I really should have used this. But here's what I'm going to say. I'm going to say the change in kinetic is 0. Now, that's not quite true. That's only true once the circuit is turned on. Once the circuit is turned on, the charges are so packed together, like people standing in lines so packed together so that your chest is pressed against the person in front of you that you can't, as soon as the person in the back starts to move, the person in the front starts to move. There is no change in kinetic energy. Everybody has to move at the same speed. But the split second you turn the circuit on, the charges go from at rest to moving. I should technically say the split second you turn the circuit on, there is an energy lost because the charges need some kinetic energy to get going. Once the circuit is on, though, Marissa, there is no change in kinetic energy. This is why it's bad to flick stuff off and on, off and on. When you flick stuff off and on, you are using a bit more energy than just having it run the whole time. But we're going to ignore that, Justice. I've mentioned it, but we're going to pretend all of our circuits that we're looking at are on. Okay, so I wrote here, once flow is established, charges flow at a constant speed. Not very fast, actually. You might think, oh, the charges flow at the speed of light. Actually, in a circuit, the charges flow not that much faster than someone walking. But because they're so packed together, it seems instantaneous because as soon as you push on the back charge, instantly that front charge moves through the circuit because they're so packed together. But actually, you can calculate current speed. It's not very fast. So, anyways, long story, this little preamble says we're going to ignore the change in kinetic. Let's crunch something. And you know what? Since we're starting out, let's fall back on our Physics 11 DFIC approach. I don't need to dulp. I don't need to draw a little picture. They've shown me one. Looking at example 3. Emma, my joy, what are they asking me to find? Find the... Oh, so I'm going to do my usual I equals question mark. And I'm going to do my usual, hey, let's look for other physicsy words and or numbers. I see a 1400. What are the units next to the, what are the units next to the 1400? So what is that? Current, voltage, what's measured in watts? Yep. What else has this question told me? You have to go look at the circuit itself. They've told me something in the circuit. 120 volts. By the way, folks, what does that AC stand for? It's alternating current. That's what's coming out of your plugs. So in this question, you're plugging a blow dryer in, a 1400 watt blow dryer, into a 120 volt circuit, which is what we get from your standard plugs. How many amps will it need? I'm looking for an equation that has a P, an I, and a V in it. I think there is one. In fact, Emma, could you get the I by itself from the previous equation that we wrote in the box in terms of power and voltage? You're going to have to go back a page, right? Our Joule's law in the box. You got it there in the box? Get the I by itself. So P equals VI. Rewrite it for me, my joy. Yeah. Yep. It's just that easy. How many watts? 1400. How many volts? 120. How many amps? 11.7. Now, a standard plug will break, will overload, will trip a breaker at 15 amps. Could you run 2 blow dryers on this outlet? Nope. In fact, the maximum I have left, I can even do the math once my computer boots up, once my calculator boots up. If I go 15 amps, which is what a standard outlet can handle, minus 11.7, I can handle 3.3 amps. In fact, since I know it's plugged into 120 volts, the maximum I can put in is a 400 watt. In fact, a 400 watt appliance will trip the breaker. A 400 watt appliance will trip this breaker. Okay. By law, electric devices must have the wattage printed on them somewhere. So I have here a little chart. We're going to do our mix and match because I always like to give you an idea of what's really big and what's really small. So on the left, I have several appliances. On the right, I have some scrambled wattages, power ratings. Here is your hint. The more heat a device moves around, the higher its wattage, because we said earlier that wattage power was energy lost going through a resistor. So looking at those appliances on the left, which one moves around the most heat? It's one bigger than that, actually, Jake. Nope. Clothes dryer. In fact, a clothes dryer, if you pull it off the wall, is plugged into a different type of an outlet. It's actually got a special circuit just for it. That and your stove are the two that have a special circuit just for them. And they take a 240 volt outlet, not 120 like our standard, and I think it's a 30 amp circuit. So biggest wattage, clothes dryer usually has about 5,000 watts. Looking at the remaining appliances, which one moves around the least amount of heat? And your hint is it will run off a small battery for about a year. Yeah, little wall clocks like the one behind me. Those take about 0.1 watts. They generate almost no heat. Oh, I know an average light bulb. What's the wattage of an average light bulb? I'm going to assume you've all replaced at least one in your life. Okay, so average light bulb is going to be about 60 watts. I can cross that off. Which item do you think moves the next largest amount of heat? Jake, this was your original guess. Hot water heater. Now that's assuming it's an electric hot water heater. Here in BC, a lot of ours are natural gas-powered hot water heaters. Okay. Microwave oven. Oh, what does it say in brackets, Carly? Large. There's large microwaves and there's small microwaves, and they generate different wattages, which is why whenever you're looking at the instructions to nuke your food, it says microwave oven times may vary. Okay? They don't know what kind of a microwave you have. Small microwave, 800 watts. So what's a large microwave? About 1200. Or 1.2 kilowatts. Then we're down to a computer and a kitchen fan. Which one of these generates the most heat? I'll give you a hint. It actually needs a fan built inside of it to cool it off. Computers usually pull about 800 watts or so, give or take. Kitchen fan, you can feel if you have your kitchen fan running, put your hand on the motor and you'll feel it's warm, not hot, but it's yeah, warm. Okay. Gives you an idea of what's big and what's small. In fact, now let's talk about energy use. This is what BC Hydro charges you or your parents, you once you move out and start paying your electric bill. BC Hydro charges you not for how many watts. BC Hydro charges you for how much energy you use. And since power is energy over time, I guess that means that energy is going to be power times time. Mr. Dueck, you used PE for, yeah, I did, but now I have a P in the equation. You know what? I'm going to actually use E for energy this time. How about there? Electric potential energy is power times time. Problem is, a joule is very small. Most of you, if you looked at your parents' bills for BC Hydro, if it was given in joules, their bills would be in the hundreds of million joules or in the billions of joules, and that would freak people out. And also, people don't have a good understanding of big numbers like that. So we actually use a larger unit called the kilowatt hour. By the way, what's hours a measure of? What does hours measure? Time. What does watts measure? This is power times time. Same equation, different units because you get much smaller answers this way. 1 kilowatt hour is 1,000 watts times 3,600 seconds. You know what? 1 kilowatt hour is 3.6 times 10 to the 6th joules. Here is my conversion factor. Typical household uses about 1,000 to 3,000 kilowatt hours per month. Let's crunch some numbers. Let's leave a 60-watt light bulb on all month. You know what? Let's make it a 30-day month because 30 days has November, whatever, because months have different amounts. 24 hours per day. We're going to find the amount of energy that it uses in joules. We'll convert that to kilowatt hours. And then BC Hydro, assuming it charges about 6 cents per kilowatt hour, I think now it's about 7 cents per kilowatt hour. See how much money it costs. And we're going to run into a problem. First of all, it wants us to calculate the amount of energy in, well, energy is power times time. How many watts of power? 60-watt bulb. How much time? 30 days times 24 hours per day times how many seconds in 1 hour? 60 seconds in an hour? Oh boy. Now I know why you're late so much. Sorry, what? 3,600. Explains a lot. 1 light bulb, how many joules of energy will this take? And I'm getting a lot. That's one bulb. You can imagine if this added up, parents or adults would freak if they saw this on their bill. I'm going to write 1.56 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. But I'm going to keep this number on my calculator because part B says convert to kilowatt hours. Hey, this is a Physics 11 unit conversion, and those of you that had me in Physics 11 may remember whenever I did a unit conversion, what's the first thing that I always did just to relax myself? I wrote down what they gave me. Now I'll write down the whole thing. 5, 5, 3 5s and a 2. Now this is in joules. So I guess that means I want joules to cancel. So where do I want joules to be in the second fraction? On the bottom. I want kilowatt hours on the top. Oh, is there a conversion factor? Oh yeah, 1 kilowatt hour is the same as how many joules? What did I say? 3.6 times 10 to the 6th. So I guess it's going to be divide by 3.6 times 10 to the 6th. 43.2 kilowatt hours. A much nicer number. So, if you left a light bulb on non-stop for an entire month, what would that cost? Well, the cost is going to be the number of kilowatt hours, 43.2, times how much it costs per kilowatt hour. In dollars? Some of you who had me last year may recall a Verizon phone video about a guy trying to explain the difference between $0.001 and $0.001 and not succeeding. $2.59. And this is the problem. Really, that's not exactly throwaway money, but all of you could afford to leave a light bulb on for an entire month, 24/7. We're too good at making electric power for cheap. There's not much of a financial incentive to shut stuff off. So why are we telling you always to shut stuff off? It's not for the money. I mean, that adds up, sure. If you had 10 light bulbs, that would be $25.90. Okay, that adds up, but why do we tell you to shut power off, shut appliances off, shut things off? It's not really to save energy. It's a secondary feature. Okay, I'll give you that. Saving energy, why? Why do we need to save energy? Okay, sorry? It's the whole environment thing. So in the 1930s and 40s and 50s and 60s, first of all, where do we get most of our electricity here in BC? I'll give you a hint. We don't have coal-fired plants like they do out in eastern Ontario, for example. Okay, we have BC Hydro, which is essentially we get our energy from nature by pulling energy from gravity, letting water run downhill. And once you have it set up, it's pretty clean. So we built a bunch of dams in the 30s, 40s, 50s, and 60s. And hey, clean energy. Although in hindsight, we learned, first of all, we really wrecked our salmon runs. When I was in elementary school, in grade 3, which would have been 1978, we were asked to do reports on BC's biggest industries, and we got a list of the top 10. And I picked our third biggest industry. And our third biggest industry when I was 8 years old was salmon fishing. I doubt it's top 20 now. We kind of wrecked the salmon runs by, we didn't realize that damming all these rivers would change the salmon runs. We've tried to do man-made workarounds and fish ladders, and they're not the same. So we would prefer not to have to build more dams. Also, when you're building artificial lakes and flooding areas behind them, you're flooding a bunch of trees that have carbon storage, and you're gradually, over time, releasing that back into the environment. So Stave Lake, for example, if you ever go to Stave Lake and you're out on the water, you still see trees poking up out of the water all over the place, little tips of long, high trees that are, all the way, that go down, 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 all the way down to the bottom. So it's an environmental issue. What do you guys think? Is our demand for electricity in the next 10 years going to go up or going to go down from what you know of society? We like our tech toys. It's going to go up. So what we're trying to do is be more efficient with what we have. And that's my message for you. Learn to be more efficient with what you have. Shut lights off. Sort of. I'm going to contradict myself in a little bit. Turn the page. Efficiency. The efficiency of an object. Recall, efficiency was defined as energy out or power out or work out divided by energy in or power in or work in. In fact, we use the Greek letter eta for efficiency. The Greek letter eta was this little N with a tail. And it was or except that's not how I told you to learn it. Does anybody remember kind of the cheap, dumb way I told you to remember it? Sorry, what? Oh, thank you, Atla. You're the first class to get it right. All my previous 2 classes all said, oh, bigger number over the smaller number. Why can't we have bigger number over the smaller number? That would give you an efficiency bigger than what? 100. The fancy word is you'd have something bigger than unity, because 1 is a fancy word for unity. Unity is a fancy word for 1. And you've either invented a perpetual motion machine, which under our current understanding of physics is impossible, or if you actually have, 5 years from now, you'll buy Bill Gates. You'll be wealthy beyond your wildest beliefs. So I'm going to write this. Because this is the unit where you will somewhere in your future see a question where the word out appears in front of the bigger number, just grammatically. And the word in appears in front of the smaller number. And every year, I have a couple of kids trying to tell me that the answer to that question is whatever, and I'm being very vague on purpose. It's 136% efficient. No, it's not. It's really not. Can't be. Oh, the other thing, though, Justice, I'm going to say, make sure your units match. So make sure it's joules over joules or watts over watts. And then times 100% to make it a percentage. A little math aid. You know what? Let's do a question. A 60-watt light bulb is connected to 120 volts AC, alternating current. It produces 58 joules of heat and light every second. It's left on for 8 hours. Electricity costs 6 cents per kilowatt hour. Found. Okay. Current through the bulb. All right. Sam, what does part A want me to find? Current. Oh, I equals question mark. Now, I have 3 equations that have I in them, but I told you that first one we're hardly ever going to use. Reading the data that they gave me, can I use Ohm's law or Joule's law? Well, I think I can go power equals 60, right? Voltage. Hey, Emma, this is just like your question earlier. I think we're going to go current equals power divided by voltage, 60 over 100. You know what, Sam? I think even you can do this one in your head. Can you go 60 divided by 120 as a decimal? Don't let me down. Thank you. I'm going to go to 2 sig figs. So, Sam, I'm going to go to 0.50 just because I have 2 or 3 sig figs. Units, what's current measured in? Amps. You okay with that? Cool. Hey, Kyle, what's B want me to find? Resistance is not futile, it turns out. We can find it. Which equation had R in it? Can you get the R by itself, please? And this is if we know 2, we know 4. Since we know power, and we know, in fact, we know 3 things now. R equals what? V over I. Kyle, what's the voltage source in this question? 120. What's the current in this question? Dividing by 0.5 is the same as multiplying by? So what's the answer in your head, Kyle, my friend? 120 divided by 0.5 is 240. What are the units for resistance? What are the units for resistance, Kyle, my friend? Ohms. Very good. Mr. Dueck, you keep that just for such an emergency?
Maybe.
Yeah. Walked right into that one. Efficiency. Now, efficiency is going to be the smaller number divided by the bigger number, or power out divided by power in. I know we're putting 60 watts in. The problem, what are the units next to that 58? Can you read to me that whole sentence, Carly, starting with the word it?
It produces 58 joules of heat and light every second.
Every what?
Second.
Every what?
Second.
That's actually watts, because they have if they hadn't added that phrase, I couldn't do it. But every second, that's actually saying 58 joules per second. Oh, that's work over time. So even though they said joules, 58 joules every second is 58 watts. Oh, and then times 100 to make it a percent. You get 96.7%? Wait a minute, Mr. Dueck. You're telling me that incandescent light bulbs are 96.7% efficient? I thought they were terribly inefficient, Mr. Dueck. In fact, haven't politicians in Ottawa decided that they're going to phase out incandescent light bulbs? And you're starting not to see them in stores. They want to replace them all with those spirally fluorescent ones. Bad science. So, put your pencils down. I got to go on a rant. It is true that most of the energy of a light bulb, of an incandescent bulb, goes into heat, not light. But if that bulb is inside, that heat's not wasted. Your heating bill is lowered by exactly the amount of heat that that bulb gives off. It's not wasted in your house. And the politicians didn't realize that, oh, it gives off lots of heat, that's inefficient. Well, wait a minute, Mr. Dueck. In the summertime, we don't want to heat up the... Okay, that is true. In the summertime, we don't want to heat our house up. Holly, what country do we live in? We have a nickname for Canada. We call it the Great White North. In the Northern Hemisphere, in Canada, in the summer, are our days longer or shorter? Do we use light bulbs more in the summer or less in the summer? Significantly less. So I'm not sure how much of that heat is going into. It is true that that part is wasted energy. Hey, Mr. Dueck, wait a minute. What about outside, Mr. Dueck? You know, if your light bulbs are outside in the winter, now you're just heating up the air. You can't use the fluorescent bulbs outside very well. They don't deal with humidity and cold changes very well. And there's a problem with these fluorescent. With these, there's a problem with these. And the problem is every one of these, every one of the little spirally bulbs contains a little bit of mercury. There's a mercury switch. So when I said to you earlier, it's a waste, my rant about always shutting things off to save the environment, for these actually, for these types of lights, these fluorescent bulbs, it's better to leave them on all day, because what wears out is the mercury switches. And I've been by dumpsters at businesses and I see these sticking out of dumpsters. You should not throw the spirally fluorescent or these long tubular ones in the regular trash. That mercury ends up in the environment, and we have no technology right now to remove that mercury from the environment. All of you right now have far more mercury in your system than your great-grandparents did. And it's measurable. It's measurable. Because it goes into the oceans, fish eat it. Girls, you probably know this, and if not, all of you, once you start having children, will know that pregnant women are told to avoid seafood because the whole mercury thing, right? We don't have any technology to get rid of the mercury in your body. So, while the politicians meant well, we're going to force everybody to use the little spirally fluorescent ones. I don't think it was good thought out science, because those bulbs are not as inefficient if you look at the overall house picture. Yes, they're terribly inefficient if you're just asking how much of the energy goes into light. Then the answer is about, I think, 12%. The rest is heat. But here in Canada in the winter, that's a good thing. In the summer, that's a minor thing. And that mercury is an issue. So, end of rant. Bad science. But they meant well. D. How much energy? Oh, energy is power times time. How many watts of power are we using? We're getting out 58 watts, but we're using 60. How much time? 8 hours. Oh, no, that's wrong. I can't just time. I have to change the hours to what? Grant, how many seconds in 1 hour? Oh, boy, thank you. So leaving this bulb on for 8 hours is going to use 1.73 times 10 to the 6th, 1.73 times 10 to the 6th joules. You know what? I'm going to convert this to kilowatt hours right now. So I'm actually going to divide by 3.6 times 10 to the 6th. And the reason is the next question wants cost, and I calculate cost using kilowatt hours. So since I have this on my calculator, 0.48, just about almost half a kilowatt hour. And again, let me emphasize, although kilowatt hours does have the word watt in it, it's not a measure of power. It's actually power times time. It's a measure of energy. It's the industry standard. Joules is the science standard. Kilowatt hours is the industry standard. How much will that cost? Cost is going to be 0.48 times 0.06. And again, like I said, our problem is we're too good at creating electricity for cheap. How much will it cost you to leave this bulb on for 8 hours? About 3 cents. There's no financial incentive. People are too lazy to go upstairs and switch off a light bulb for 3 cents. Now, thankfully, most people don't realize that energy is this cheap. And even if they do, like you guys, why are we turning the lights off? Not to save money, but to save the planet, which I think is a better idea. Is that okay? What's your homework? Lesson 1, if you haven't finished it already. Said I was going to try and give you about half an hour. You're going to get a full half hour. Now you can also study for your calculus test. Number 2. Number 3. 4 is good. 5 is good. So right now I've assigned 1, 2, 3, 4, 5. I'm going to pass 6, but I love hot dogs, so how can I skip number 7? How long will it take to cook a hot dog? Now, if you look at number 8, it is saying find work done. Oh, this is orbit, that's review. Number 9, hill energy, that's review. Number 10, number 11. We're going to start to do review because we only have, I think, 21 classes left. Yeah, and then you're out of here. But I'm not going to be assigning review in this unit. I'm going to start to flog review, and then I'll start to assign some of these review questions over the next few units, though, because we're not that far away from the end of the year. In fact, in a couple of weeks, I'm going to be giving you all 4 or 5, I can't remember, a bunch of old provincial exams, complete with answer keys, and that's going to be what you can also use to study, because my tests are based on old provincials, and that's kind of like, hey, everything in the course all at once, they're good practice. You have, oh, wait a minute, I have a short video to show you.